Now, if you move 10 degrees over, the way it should be done is, let's say every two marks is 10 degrees. It should be plotted like this on a flat Earth, with everybody on the flat Earth looking at the same point in space, where Polaris is.
Hold on, that's not what the data tells us. So you claim you're looking to the same point in space, living on a ball, looking to Polaris, while the data say you can't?
Now, the proper way to do it is like this.
That's a nice trick, Shawn. Zooming out, and then all these lines appear to go to Polaris. Let's put all these azimuths from these locations in an orthographic front view. And this is Polaris at the 85th latitude north, which at an angle of 7.2 degrees. So now let's see how that looks like. Holy shit! Shawn, where is your Polaris?
So that was Qnfee trying to debunk Shawn Hawkins, saying Shawn was wrong and criticising him for not using the official altitude and azimuth data from sources such as the USNO website. Q often tries to demonstrate that the globe model is false, and that's because he can't successfully transfer this official data to various points on the globe and get the resultant lines to converge at a single point. So in this video, I'm not even going to bother looking up the altitude and direction data from any official source, and that's because I'll acquire this information naturally from the globe geometry. I'll then get multiple observers to simultaneously view a single point out in space, and we'll see that their observations match the official data accurately and without any conflict whatsoever. Let's start by going through what we have on screen. We have a sphere with a radius of 6371 kilometers. There are 3 observers A, B and C on the prime meridian, and this table shows their coordinates. Star presets, we have one for Polaris and one for Capella, telling us where the star is directly overhead on May 21st, 2024 at 0610. This is the star, and this is the geographical position. The star's distance is controlled using this slider, and currently it's about 10,000 kilometers from the Earth's centre, so we'll leave it local for now. The other sliders allow me to just change the positions of the observers, or to change the position of the star, should I feel like it. So the first thing I needed to do was to get these HC values for points A, B and C. So let's scroll down here. That's this section, and in the case of point A, it's 90 degrees minus angle AOGP. So let's draw that in. If we do a vector from O to A, that's that one. A vector from O to the GP, that's that one. So we do the angle between U and V, and we get a result. So that's our angle. So if we have 90 degrees minus this angle, that's our HC value for point A. Let's get rid of that. So the next step is to get these ZM values for points A, B and C. This is our azimuth angles. And what I'll do is I'll switch off points B and C, and we'll just focus on point A. So we'll need a vector from point A that points in the direction of the star. That's this one, and that's this line. So I've called it A to GP. Now this vector does point to the star. It might not look like it, but it does. And if we click on it, we can see that it does. And this follows a great circle path that will get us directly underneath this star. In fact, we can draw that in. It'll be intersect path. So that'll be a plane OA and the GP with the sphere. So So that's our great circle, and you can see that the shortest route between points A and the GP is along a great circle, and this vector here is tangent to that circle. So, and it's in the direction of that circle. So let's get rid of that. We don't need that anymore. And now we want to do a similar vector to the North Pole. That's this one. I've called it A to pole. And all we need to do now is measure this angle, and we should get 46 degrees. So that's that one there. And that's how we measure the azimuth angle. So that's how we acquire all these angles here. So I'm just going to switch off that. I'm going to turn B and C back on, and you can see the individual vectors now in the direction of the star. So if I center on B and on C, you can see how they individually all point to the star. Now that we know that all our observers are looking in the right direction, we'd like to know the altitude at which each observer sees the star. So let's just focus on A again, and we'll add in the other vector that we need to measure the observed angle. Currently, we're measuring 13.77 degrees to the star, and that's this value here. Ideally, we'd like it to equal this computed altitude angle that we got earlier, and the reason why it doesn't match is because this star is so very, very close to Earth. So what I'd like to do now is push this star very far away from Earth, a few hundred light years in fact. So keep an eye on this star distance value here, together with the observed altitude angle, and watch how this angle reacts as the star distance increases. So I'll quickly do that again, just so that you can see how it looks like when we include B and C. Does this mean that we've just done what Qnfee said couldn't be done? To recap then, we've just got 3 observers to simultaneously view a single point out in space at a particular moment in time without looking up the official azimuth and altitude data beforehand, and not have we only calculated them correctly using the geometry of a ball, we've also shown that this isn't a problem for multiple observers in terms of what they measure. Let's switch to Polaris now. And just to be thorough, we'll just recreate some of the angles that Qnfee used in his demonstration. So let's take observer A down to the equator. B we'll take down to 50 degrees. That's 50. We've already seen 60. He had 70 as well. Let's move C up to 85. And we also had 80, didn't we?
So you claim you're looking to the same point in space, living on a ball, looking to Polaris, while the data say you can't? No, that's not what the data say, Shawn.
Well, that's going to be it for this one. Nothing wrong with Shawn's demo in the end, and it was perfectly acceptable for anyone to place Polaris high above the North Pole when demoing the basic principle. If anybody wants to have a play, I'll leave a link to this Geogebra script in the description below. Don't forget to hit the like, leave a comment, subscribe if you haven't already, and I'll catch you later.